exam presenting the team of Russia with a report on the problem number 4 Super. Let me remind you the condition of the problem. Throw a highly elastic ball into space between two plates. Ball starts bouncing and under some circumstances can even be projected back to you. Investigate the motion of the ball and parameters influencing the motion, including the orientation of the plates. Firstly, return important initial parameters influencing the experimental result, which is the ratio of velocities after and before collision, the initial linear and angular velocity, the distance between plates, and the system orientation. We will show the results of the study of these parameters later. To explain this phenomenon, we made the following plan. Firstly, we will observe this phenomenon. Then, we will make a qualitative explanation of the phenomenon. After that, we will describe the motion of the super ball and compare our theoretical model to experimental data. Further, we will determine conditions of the ball's returning, and finally, we will investigate how plate orientation influences the ball's motion. Let's observe this phenomenon. We throw a rubber ball into the space between two horizontal plates, and as it was mentioned in the condition of this problem, it returned. Therefore, we will call the rubber ball a super ball. Then, we throw a ping-pong ball in our system. It didn't return and remained between the two plates. Therefore, this is not a super ball. We will call it a rigid ball. Why didn't it return? What is the difference between the rubber ball and the ping-pong ball? Let's start with the qualitative explanation of the phenomenon. As it was mentioned in the condition of the problem, we have to throw a highly elastic ball. What does it mean? The collision time can be estimated as the ratio of two ball diameter to the speed of sound in the ball. The center of mass continues moving during this time. The friction force decreases the horizontal velocity of the ball. In addition, the torque of the friction force spins the ball. As a result of the collision, the ball acquires an angular velocity and has a lower horizontal velocity. What happens if we throw the super ball? The center of mass continues moving during collision as well. However, it happens because of the ball's deformation. It means that with the small ball's deformation, the contact point stays in the same position. As a result, the torque of the normal force also spins the ball. Therefore, there are two torques related to the center of mass. In addition, a residual deformation spins the ball. The second collision happens with the initial angular velocity. As it was shown on the previous slide, the contact point stays in the same position during collision. We assume that the ball rotates about this point. Positive ball's rotation is opposite to horizontal velocity of the ball. The required condition for the return is following. The rotation speed should be higher than the horizontal component of the velocity. In this case, the ball changes the direction of horizontal velocity. After collision, the residual deformation spins the ball in opposite direction. And finally, the super ball changes direction of both the horizontal velocity and angular velocity. We can observe a similar behavior of the super ball if we throw it with an initial positive angular velocity. The ball changes the direction of linear and angular velocities after each collision. We made the conclusion that the super ball can change the direction of linear and angular velocities. This is the main cause why the super ball returns. So, as it was mentioned in the condition of this problem, we have to investigate the motion of the ball. In order to do this, we made a model describing the motion of the super ball. We use the following assumptions in our model. There isn't loss in energy, and the friction force coefficient between the plates and the ball is infinitely large. Firstly, we can use the energy conservation law. It means that the total energy remains constant before and after collision. In addition, we assume that the contact point remains the same. All forces acting on the ball have a zero shoulder at the contact point. Therefore, the angular momentum at the contact point remains constant. As a result, we got these expressions for vertical, horizontal, and angular velocities after collision. This approach helps us to avoid the complicated description of the ball's deformation. In order to compare this model to experimental data, we wrote the computer simulation program based on this solution. It predicts the trajectory, the velocity, and other parameters of movement for super ball for various initial parameters. We built the following experimental setup to perform the measurements. It consists of a high-speed video camera and two horizontal plates. In our experiments, we used the rubber ball and the ping-pong ball with the same sizes. In order to trace the ball, we used the Pascal capstone program. It allows us to reconstruct the ball's position, velocity, acceleration, and rotation. We used it to compare theory with practice. We threw the super ball into the system and reconstructed its trajectory. We used the same initial parameters in our computer model, and as a result, we got the similar ball's behavior. However, comparison of trajectories shows significant differences. Let's consider this result. In the experiment, the third collision happens in the space between the first and second collisions. However, in our computer model, the third collision takes place outside of this zone. As it was mentioned before, we assume that there isn't loss in energy. However, there is an energy loss of the real ball due to a small slippage and the ball's deformation during collision. Taking into account the energy loss, let's define the restitution coefficients as a ratio of velocities in the contact point after and before collision. As a result, we got these expressions. The gamma is the vertical restitution coefficient and beta is the horizontal one. Resulting of energy conservation, you can see at this slide. Both the restitution coefficients are equal to unity. Decreasing the vertical restitution coefficient results in exponential decreasing of the trajectory height. Decreasing the horizontal restitution coefficient provides a trajectory similar to experimental one. To determine of restitution coefficients, we build the experimental setup. It consists of a channel whirling and inclined plane. The vertical restitution coefficient can be determined by experiments with various vertical velocity before collision. To determine of horizontal restitution coefficients, we made experiments with various horizontal velocity in the contact point before collision. After that, we reconstructed the dependency of vertical velocity after collision from one of before. The vertical velocity after collision is proportional to one of before. As one would accept, the vertical restitution coefficient remains the same. Its average value you can see in this slide. After that, we reconstructed the dependency of the beta from the contact point's velocity. As you can see, the horizontal restitution coefficient is slightly decreasing with increasing of the contact point's velocity. We can assume that with a small deviation of the velocity during collision, the horizontal restitution coefficient is a constant quantity. Its average value you can see in this slide. We use these values of restitution coefficients in our computer model, and after that we compared the experimental trajectory with our computer simulation. As you can see, predictions from our computer model has an excellent agreement with the experimental data. So, to check our model, we made a lot of experiments with various initial parameters, and we always had an excellent agreement of the experimental trajectory with our computer model. It allows us to use this model for describing the motion of the super ball under any initial parameters. So, our computer model allows us to reconstruct the trajectory of the ball. It means that we can determine conditions of the ball's returning. We concluded that the very important parameter influence on ball's projected its horizontal restitution coefficient. For example, we can throw the super ball with a lower horizontal restitution coefficient, and as you can see, it doesn't return. And if we throw the super ball with a higher restitution coefficient, it always returns. And the other parameter influence on projection of the ball is distance between the bottom plate and the ball. These two parameters determine the condition of the ball's returning. And if we throw it with a small distance to the bottom plate, it returns. And if we throw it with a long distance, big distance to the bottom plate, it doesn't return. So we reconstructed the dependency of the minimum horizontal restitution coefficient necessary for return from the distance for bottom plate. And if the horizontal restitution coefficient is less than necessary for return, the ball doesn't return. If the horizontal restitution coefficient is higher than necessary for return, the ball always returns. By this map, we can estimate the result of the experiments. So when we throw the super ball with a higher restitution coefficient, we can see that the ball collides very often and remains in the space between two plates. If we throw it with a lower horizontal restitution coefficient, it returns after 3 collisions. It's very interesting. We get the lower horizontal vertical restitution coefficient necessary for return in the real case. We throw the super ball with a lower vertical restitution coefficient, and as it predicted our computer model, it returns after 3 collisions. We estimate the vertical restitution coefficient, and we got the very interesting result. The minimum horizontal restitution coefficient necessary for return is much less in real cases than in perfect one. And so, by this map, we can estimate the result of the experiments. In the condition of this problem, we also have investigate parameters influencing the motion, including the orientation of the plates. For example, we can rotate the system 90 degrees, and it turns out that it influences only on ball's trajectory. Therefore, we can determine these types of motion by our computer model. So we can make an experiment with non-parallel two plates. So can you play this video? We threw the super ball between two two non-parallel plates, and in this case the ball can return 2, and we can make the same experiments in our computer model. So we can see that the ball returns after 3 collisions. So can you play? We can also make an experiment with with a parallel with negative angle which is other, and in this case the ball has a lower chance to return. So let's make the conclusions. We can make a qualitative explanation of the phenomenon. After that, we described the motion of the superball by energy conservation law and conservation of angular momentum. In order to compare this model to experimental data, we wrote the computer simulation program based on this solution. It predicts the trajectory, the velocity, and other parameters of movement for superball for various initial parameters. However, the comparison of trajectories showed significant differences. In order to take into account the energy loss, we introduced the restitution coefficients as a ratio of velocities in the contact point after and before collision. And after that, we got an excellent agreement of the experimental data with our computer simulation. It allows us to use this model for describing the motion of the superball under any initial parameters. So we determined important 2 parameters influence on both motion, and we determined the required condition for the ball's returning. If the horizontal restitution coefficient is less than necessary for return, the ball doesn't return. If it's higher, the ball always returns. And also, we described the motion of the ball with non-parallel 2 plates by our computer simulation. The reference list is following. I hope you get enjoyed. Thanks for your attention.
Okay, questions by the opponent, please.
So you said that, answer quickly, please. So you said that angular momentum conserves.
Yeah.
So did you consider the deformation of the ball when you used the rigid body equations?
Yes, there is small deformation. You can see.
No, okay. And thank you. And the radius of duration during the collision is constant. The radius of duration of the ball, the moment of inertia of the ball.
Yes. Oh no, yes,
No.
it can depend. But
Let's discuss it back on the time.
we can neglect here.
Okay, thank you. So as you said that there is conservation of angular momentum, we're talking about the point of contact of the ball and the plate. Yeah? So didn't you consider the displacement of the normal force?
Displacement.
You put on the slide the
there is small displacement. Yeah.
It could not alter the angular momentum during the collision. So this is assumption valid, as we have a torque of the normal force displaced during the collision.
There is the torque of the friction force and torque of the normal force relative to the center of mass, and it's
relative to
this
the point of contact where we are considering the
it's exit on the ball on the contact point. Yeah.
And one more some questions. Is this an area of contact or a point of contact?
There is small area of contact.
Okay.
Yeah.
So you consider the conservation of angular momentum in relation to which point of this area?
So we can. Yes, the center of the area.
The center of this area.
Okay. Yeah.
So you said that you tested with ping pong balls, considering it a rigid body, yeah?
Yeah.
So didn't you consider that the ping pong ball could deform during the collision, as it is made of plastic, and plastic is not totally rigid?
Plastic has a smaller elasticity.
Did you test it with hollow balls?
What?
Hollow balls, as you change the rigid configuration?
Oh,
No more time for
I
next.
see. I didn't follow.